Good morning. We are set to finish up Chapter 8 today, and the topics that we're going to be looking at in this last portion of Chapter 8, we're going to be looking at gravitational potential energy and long range, and then we're also going to be looking at something called power. So power is really important in physics. So definitely we don't want chapter fatigue to set in. So give yourself breaks because all this stuff in this chapter is important. So this later stuff in the chapter, it's not just toss away stuff. This is kind of central to the ideas that we're presenting in these chapters on energy. So let's go ahead and get started. So gravitational potential energy we have already defined. But remember, the gravitational potential energy formulas we've used so far are only involving a fixed, uniform gravitational field. So the gravitational potential energies we use for the roller coasters and for dropping the rock, those assumed that the gravitational field, little g, is a constant. And if we're going to do rocket science, if we're going to launch things out into space, well, the gravitational field's not going to be constant. We're going to have to come up with a more general formula. Now, we did this in Chapter 6. Remember, we kept saying the force is mg, force of gravity is mg, and then in Chapter 6 we said, but wait a minute, if we think more carefully, the force involves both objects, both of their masses, and the distance between them. Well, gravitational potential energy is going to apply to that. So let's take a look and see. Now, here is the formula. Let's just go ahead and write that up front. I think that's a good idea that we're doing that. The formula for gravitational force, oh, I guess we haven't done it. I'm sorry. This is just the force formula so far. So we haven't got the potential energy, but we will soon. So the force here is given by g m1 m2 divided by distance squared. Now they're specifically looking at an example here of a satellite. So here's a satellite in orbit, and it's traveling not a circular path. So it's traveling through space from point 1 to point 2. How do we determine differences in potential energy between point 1 and point 2? So what we can do, now this is in kind of full-blown vector notation. What we can do is we can start with this force formula. Now they've put a unit vector here. The unit vector is pointing away from the location of the center of the Earth. The distance, remember this is distance, it's not radius, the distance between the center of the Earth out to where the object is located, that's changing. So how much we need to come in and we have a formula that tells us how the force is varying from one point to another. What we want to do is come up and ask ourselves, how much work would we need to do if we were to move the satellite at point 1 and move it all the way to point 2? Okay, so now what happens with the large-scale formula here? It's kind of like what we looked at before, in that it really depends on elevation. So it's not so important the path that was taken here. The important question is, what's the R value here? And what's the R value here? We can come back to the formula for work that says if we follow the force going from point 1 to point 2 needed to the force of gravity that's pulling on the object from point 1 to point 2, if we keep track of that all the way, we'll be able to come up with a formula. So I think the approach here is a bit over the top. I think we can do this more simply. Let's take a look and see. So when we solve those integrals, I'm going to come back to here and say that the work that we have to do then would be gmm over r squared minus gmm over r1. If you remember, The force formula has an r squared in the bottom. When we integrate the r squared, we're going to get 1 over r. So long-range gravitational forces are going to be given by gmm over r squared. The potential energies are going to be given by gmm over r. Now, we're not quite at potential energy yet. What we're at so far is the work. And what we can say from that is that the potential energy will be the negative of the work that's done by the gravitational force as it moves from one location to another. So I'm going to say these diagrams aren't necessarily the best. We're going to come back and I'll draw some more and see if that helps. I mean, this is looking at the vectors in a lot of detail, and that's fine, that's good. I think maybe the better approach with this, looking at the derivation is great, but let's take this formula, now that we have it, and actually try to understand why this is the correct formula for gravitational potential energy. So the gravitational potential energy at a location r is given by gmm over r, where r is the distance from the center of the Earth out to where the object is located. So r would be measured from here out to here. For point 2, r would be measured from here out to here. And all of the details of the dot products and in the work calculations, that all goes away. Does not depend on the specific path, only depends on r. So this is what the function looks like. Now, what this is suggesting is if we have an object out in space, we have a satellite or something, its potential energy is going to keep increasing as it gets farther and farther away. What is the highest potential energy it could possibly have? And there's actually an asymptote for that. And strangely enough, if r approaches infinity, the potential energy approaches 0. Now, this takes a little getting used to. Fortunately, but we've already been practicing this. We've already been practicing the idea that gravitational potential energies can be negative or positive. Well, when we use these long-range forces, the potential energies are exclusively negative. And here's how it works. If I have two objects and they're gravitationally attracting each other, where would I get the most potential energy? And for an attractive force, pulling the objects apart stores up more and more energy. In the example we had here, one of these objects was the Earth and the other one was a satellite. So another way to view this is, where would the satellite be located such that it has the highest possible potential energy? And it would be located at infinity. Now you might think, well, at infinity, doesn't it have an infinite amount of potential energy? And it doesn't. It has a finite amount. And the reason why is that the gravitational forces drop off with distance. You guys have seen this in your calculus class, right? You do these integrations out to infinity, and if the function is dropping off rapidly enough, you get a finite answer. And that's what happens with gravitational potential energy. So what that says then is, by definition, we are going to say that at infinity, the gravitational potential energy is 0. That's where we take the two objects and we separate them far, far, far away from each other. And then as we let the objects come together, the potential energy drops. And dropping from 0 means that it will go negative. And so as we get the objects close, r is keeping track of the distance. As that satellite comes closer and closer to Earth, it's got more and more of a potential energy well. Or it's more in a potential energy debt. There's more and more of a binding energy, are different ways we express this. So if the satellite comes close to the Earth, there's more and more of a binding energy, and binding energies are negative. In order to separate away from Earth, a spacecraft would need to be able to carry out some kind of work. It would need to be able to come up with a force that could push it farther away from Earth or whatever planet or whatever star it's trying to separate from. So here's another way of looking at this. Here, gravitational potential energy. Again, this is Earth right here, but it could be something else. Let's say it's big M. And here is some object, little m. And there's two ways we can look at this. What we can do is, let's take the object at point A, and let's bring it farther and farther away from Earth until it's at point B. Now, at some point, we're going to let point B represent infinity, maybe infinity and beyond. And so the potential energy here, by definition, we're going to say is 0. So let's ask, how much force would we need from our propulsion system? Let's say that we have a propulsion system that just stays on, and that the propulsion system that we have is just enough to keep the spacecraft at constant velocity. Well, the spacecraft is consistently being pulled back towards Earth, but the force acting on the gravitational force acting on the spacecraft is equal to big G, big M times little m over r squared. So it says that mg is getting smaller, g is getting smaller. The gravitational field of Earth gets smaller as we push the satellite away. That means we can back off on the engines. So at first the engines are producing more force, and then less, and then less. And once we're out at infinity, we just turn the engines off. We don't need the engines anymore because the gravitational force has dropped to 0. All right, so how much work is the propulsion system of our spacecraft, how much work does it have to provide to take us all the way from point A out to point B? And if we integrate the force, dr, that's how we're calculating the work, we're going to get the gmm comes outside, but we're left with dr over r squared inside, and we're going to run the limits between some value of r and infinity. Now, little r, point A could be on the surface of the planet, but it could also be starting out here, so I'm going to leave it at some random location out here. When we carry out this integration, we are getting gmm times minus 1 over r evaluated between r and infinity. Now, when we evaluate that integral, what I'm going to do first, here is a trick. I don't know how much of a trick this is. If you reverse the limits of integration, you can remove a minus sign. Now, I don't know how much minus signs cause problems for you when you're problem solving. For me, a minus sign, they start to accumulate. You got minus signs, and then you're subtracting minus signs, and at some point I'm getting myself confused. So whenever I can eliminate a minus sign within an integration, I usually do. And it usually makes it easier for me to think about it. So I'm taking out the minus sign, I'm reversing the limits of integration. I'm now integrating from infinity to r, and when we carried out that integration, we ended up with this right here. The amount of work we would have to do to take an object, a spacecraft, from point A and push it all the way out to infinity, that's given by gmm over r. It's not r squared, it's just r. Forces are in r squared, energies, gravitational energies, are in 1 over r. And so if the force we were operating with was gmm over r, well, what was the work that the gravitational force was doing the whole time? And that would have the opposite sign. Remember, we balanced forces. So the work being done by F on the object, it didn't make it go faster and faster because gravity was taking out energy at the very same rate. So at the end of the day, going from A to B requires this much work due to our propulsion system, and gravity is going to take all of that and remove it and store it as gravitational potential energy. What that says then is, in order to reach infinity from point A, we have to overcome that much of an energy deficit. And so the energy deficit means we put a minus sign in. So the gravitational potential energy at point A is given by minus GMM over R. Again, let's think about that. If the potential energy here is 0, and that's our goal is just to reach 0, right? We're working exclusively in an energy deficit. The potential energies are all negative. So I start off at negative GMM over R. That's my gravitational potential energy deficit, or debt. I'm going to need this much energy to overcome my energy debt. And so that's the formula for gravitational potential energy. So I don't know, for me this is easier to think about. If you want to go back and do the more careful vector analysis, that's fine. But since gravitation is we've established it's a conservative force, this will work. So we can use this formula anywhere between the surface of the Earth and infinity. Now if we drill a hole and go to the center of the Earth, it gets more complicated. I don't think we're going to do that. But if you guys have questions on that, stop by office hours. It's kind of a fun problem to take a look at. But that's what we've got going on here right now in terms of potential energy formulas. So that's it. Now, how does this compare then? Remember, the gravitational field is given by Gm over r squared. If we're at the surface of the Earth, then r is equal to big R. And if we are looking at locations at different elevations near the surface of the Earth, we've been using a formula of mgh. How are we going to start from this formula and come up with these? How are we going to relate these formulas? Which one should we use? Should we use mgh or should we use minus gmm over r? Mgh is very useful on short distances. What we can do is we can take this expression right here and we can take some derivatives. If I take derivatives of both sides, the left side becomes du, and the right side is going to become, now this is r to the minus 1, so the minus 1 comes down, cancels the minus sign. This is going to become gmm over r squared dr. That's what the difference in potential energy will be as we move away from Earth. This is actually the force, gravitational force times that distance. Now what we can do is we can take the gm over r squared, separate that out, and turn that into g. Meanwhile, what's dr correspond to? And for short distances, dr we're going to designate as h. So back in the early part of the chapter, when we said the gravitational formula for potential energy is mgh, we were really using an approximation based off of the general formula. So the difference in potential energy over a short distance h is given by m times g times h, where we're treating the gravitational field as a fixed value over those short distances. All right, so let's drop some packages from high-speed rockets, right? So in this example, we're going to have a rocket headed away from Earth. We're going to drop the package. It says here that it's a box of empty film canisters, and we just throw it out of our rocket and allow it to fall from the rocket, and the rocket's traveling away from Earth, 1,800 meters per second, and it's at a location above the Earth's surface of 1,600 kilometers, and the package falls, it eventually falls to Earth, estimated speed at impact. So when it impacts, how fast is it going? Now we're going to ignore air resistance, which unfortunately is just not a good approximation if you're going to let something come all the way back down and hit the surface of the Earth. But let's go ahead and do that. Let's remove the atmosphere for now. All right, so the first thing we got to do is this. That 1,600 kilometers is measured from the surface of the Earth. That's not how the formulas work. So what we need to do is say that here's the surface of the Earth at 6,370 kilometers. That's right there. We're going to call that little rb. And then where we're dropping from is right here. So we're going to drop this from point A. Now, point A is 1,600 kilometers above the surface of the Earth. So if I add those numbers together, if I add together the radius of the Earth plus the 1,600 kilometers, I get 7,970, and that's what we have to measure from. So I've got to measure from the center of the Earth out to that point. Now, I don't think I got it scaled very well, right? This is 6,370 kilometers. Okay, that's 1,600. In any case, we have to add those two numbers together to determine what RA will be. And then I'm going to say that the speed we start with is 1,800. So let's think about this. If we're zipping away from Earth at 1,800 meters per second, and we just push these canisters out of the rocket, what is it they're going to do initially in terms of their motion? Well, the canisters are moving at 1,800 meters per second. So they're going to, initially at least, head away from the Earth, and then Earth's gravity will slow them down and bring it back. Now the rocket, I'm guessing, has a propulsion system, maybe, but the canisters don't. And so the canisters are going to go into free fall, but they've been given an initial velocity that's going to carry them out, and then it will fall back. So let's set this up as energy conservation. Now, when you're out in space, if all the stuff we're talking about is out beyond the atmosphere, we're looking pretty good for energy conservation because there's no friction, there's no air resistance. So that greatly simplifies the problems, or it makes our formulas very useful instead of just kind of approximations. This kinetic energy that we have is going to be given by 1/2 m v naught squared. That's very good. Now by the time it lands, it actually has gone through the atmosphere. This is not going to be as reliable. Here is the potential energy at point A. Now the potential energy that we have is a negative value, and that's because the potential energy is relative to completely leaving the Earth, and we haven't completely left it. There's still a binding energy for the spacecraft. There's still a binding energy for the photo canisters. Why do we have photo? Why don't we just isn't this just digitized? Don't we just send the information back for the photos? Anyway, we've got this debris, these canisters, these something that we're just going to let go of. Maybe it's the lower stage of our rocket. That's going to be given by minus GMM over RA. And here's energy conservation. So kinetic energy at A plus potential equals kinetic plus potential at B. And I'm writing all those expressions in. Here's the kinetic energy initially. Here's the kinetic energy at impact. Here is the potential energy initially. Now, the potential energy when we hit the Earth is going to be more negative. That's at a lower elevation. It's going to be a lower number. And since this point is negative potential energy, but this is even more negative. So this is at a higher value, and that's at a lower value. And that is being kept track of in the formulas. So the formulas are working to keep track of that. RA is bigger than RB. That is a less negative number. This is a bigger negative number. Okay, so the masses cancel out, so it doesn't depend directly on the mass of the object that we've let go of. I'm thinking it's a lower stage of our rocket. When we cancel out the masses and we multiply it by 2, we get v squared is equal to v naught squared plus 2gm 1 over rb minus 1 over ra. So that's keeping track. These terms over here are keeping track of the gravitational potential effect. Now this is at 1,800 meters per second. That was the initial speed. And then this is the extra term, the 2gm times, I ran out of space here, times the next line, 1 over rb minus 1 over ra. And as promised, this is going to turn out to be, overall, this term here is going to add to the velocity. So we're going to be using the additional potential energy, that's going to get converted into kinetic. And so this lower stage of our rocket hits the ground at 5,335 meters per second if the air doesn't slow it down. So now I was curious, what happens if we just have something sitting here at rest and we let go of it? How would that change things? Well, if we just let go of the whatever it is at zero speed, if we were traveling zero speed, then we could ignore the V naught, and recalculating it, it's going to hit at 5,022 meters per second. Okay, just curious. And again, let's go back over what happens here. Since there's an initial velocity in 1,800 meters per second, it's going to, we could have solved for this, we didn't. We could have asked how far out will it reach. But in any case, this is going to make its way out. It's going to slow down and stop. Then it's going to head back and start picking up speed. When it goes back the opposite direction, it will have gone back to 1,800 meters per second, right? Energy conservation says if we head out, we used up the kinetic energy, converted it to potential, and then we're going to convert the potential back into kinetic. And that means when we pass this going in the opposite direction, same speed. If we had launched this stuff towards the Earth at 1,800 meters per second, how would that change things? It would still impact at the same speed, it would just get there faster. So that's kind of interesting also. But this is a good problem to look at and think about potential energies and what's going on. Maybe fill in a few more of the numbers along the way. Now, what would happen if we wanted to launch something from the Earth's surface, bring it up to a really high speed, and then turn the rocket engines off and just let it drift the rest of the way? And what if the intention here was to let it drift, what if the intention was to let it drift all the way away from the Earth so that it will never come back? So if an object's kinetic energy, initial kinetic energy, matches the binding energy we talked about, so this potential energy is negative, if we launch something with kinetic energy that matches the binding energy or the potential energy at the Earth's surface, the total energy will be zero, and that means that this object will never turn around and come back. It will just keep heading away from the Earth. Now it's going to slow down, but it's just going to keep heading farther and farther away. We call this the escape velocity for the Earth or for whatever object we're thinking of. Now, when we launch rockets, we currently do not work with propulsion systems that just get left on. If we're traveling to the moon, or if we're sending a satellite out to Saturn or Neptune or something, we don't leave the rockets on because our propulsion systems right now are based on chemical reactions. And it turns out that in terms of fuel use, it's much more effective to burn the fuel as fast as you possibly can at first, build up to a very, very high speed, and then drift the rest of the way. So when they talk about escape velocity, you don't really have to travel at this speed to leave Earth. This would be a launch speed that you would need to bring the spacecraft up to such that you can turn the rockets off and you're going fast enough that you will continue to drift away from the Earth. You'll never come back. So that's what escape means in this case. So in this example it says compare escape velocities for a rocket launched from the surface of the Earth, one launched from the surface of the Moon. And then it says compare the energies required to launch the rockets. They've got the mass of the Moon here, they've got the radius of the moon, and then they've got the mass of the Earth and the radius of the Earth. So that information is all given. Let's see how this works. So the picture looks the same, right? This could be Earth or the moon. We've got a certain radius. Here is point B. And what we're going to do here is to calculate escape velocity. We could use the formula they just showed us. But what we can also do is reverse it. Instead of asking what speed would we need to launch at in order to get out to infinity, what we could do is start at infinity and just let go and see how long it takes for the object to pick up speed and then find out what speed it's going to impact the surface at. So I'm kind of doing this problem in reverse, and I'm saying at point A, we're going to assume that we've reached the point of zero potential energy and it's not moving. Now, you know, even from far, far away, there's going to be a slight gravitational effect that begins moving this rocket. So by the time we impact at the Earth's surface, the kinetic energy will be 1/2 mv squared. The potential energy will be negative gmm over r, where r is the radius of the Earth. So I did this. I said, let's imagine that we have an object. It's just 1 kilogram. Now we can scale that up. So, but I'm going to start off with just 1 kilogram and ask, how much energy are we talking about? Now, at the surface of the Earth, if I'm thinking of a 1 kilogram object, that works out to be a negative 62.5 million joules. So for every kilogram of object that we want to launch, so we want to reverse this process, for every kilogram of object that I want to launch, I'm going to have to come up with 62.5 million joules. So that's a lot if we want to launch it so that it doesn't come back to Earth. Now we could launch something into Earth orbit, maybe a low orbit, that would require not nearly so much energy, but we're going to have to come up with this much energy for just a 1 kilogram object. Now that's the energy, so they wanted us to calculate that, how much energy would be required. This is for Earth. Ooh, we should have written that in. And then the velocity here would be 2 times the kinetic energy over the mass. Now the mass we used was 1 kilogram. And so that worked out to be their 11,180 meters per second. So that's what they had given us. Now here's the very same problem for, well, this is Earth and Moon, I guess. So what we've done here is we've kind of gone back and forth. If I drop something from infinity and it falls all the way to Earth, what is the impact? How fast will it be traveling? How much energy? And then if I reverse that and launch it out, the numbers are going to be the same. I'm going to have to launch at the speed that I impacted at in order to have it travel back out to infinity. Now notice in these problems and the problems before that we were looking at where we were dropping the film canisters or whatever, there are no times calculated here. We are not calculating how much time does it take. Those problems get fairly involved. And so again, energy conservation on a first pass, we're just looking at distances and velocities. We're not really asking you guys to do timing calculations for this. All right, this is the escape velocity then from Earth. If we launch at 11,180 meters per second, it won't come back. It'll keep, it has enough speed, has enough kinetic energy, that it can overcome the binding energy of gravity. The binding energy of gravity is finite. Even to go infinitely far away from the Earth, it requires only a finite amount of energy to get there. It does not require an infinite amount. It could take a long time to get there. All right, here are the numbers for the Earth and for the Moon using the formula that we have derived here. So we've turned it around now. We're going to launch with a kinetic energy of 1/2 mv squared. We are going to start with a potential energy deficit, a binding energy, is what we were calling it. So a gravitational binding energy, we're in a deficit of negative GMM over R. We just need enough kinetic energy to equal the binding energy, because once we get out to infinity, we don't need any additional kinetic energy left over. And at infinity, the potential energy is going to be 0. So combining these and setting them equal to 0 gives us this for the escape velocity formula. Putting in the mass of the Earth and the radius gives us the 11,000. Wasn't that what was the number? Was it 11,180? Oh, it was. Okay, I was thinking 120 for some reason. Anyway, 11,180 meters per second. And then from the moon, 2,370. Okay, so that's, that's not tiny. Escape velocity from the moon is, what is it? It's like Earth's escape velocity is 5 times higher, something like that. Putting in the numbers for all I need is the radius of the moon, or Earth, because that's where we're launching from, and then the mass. Now, in terms of binding energy, how much do we have? And for the Earth, we went through and did this calculation. For a 1 kilogram object, that would be negative 62.5 megajoules. And so, to launch something at escape velocity from the Earth, we would need to come up with 62.5 million joules for every kilogram of cargo or spaceship, whatever the mass is of that craft that we're sending out. Now, in the situation for the moon, the same 1 kilogram object, putting all the numbers in, the amount of energy we need is way reduced. So this drops all the way down to 2.82 million joules for each kilogram. In fact, that's kind of suspiciously lower. How did that happen? Check the numbers on this and see what we have going on here. Maybe I'll do this right now. So the formulas that we have, this is a good way to go in and check formulas, right? Comparing the Earth and the Moon, how did the numbers compare? And it looks like the Earth mass is, the Earth's mass is like 80 times the mass of the Moon, 81, let's say. So that would be, now it's going to get square rooted. So the Earth's mass should boost the, but we were just thinking in terms of the kinetic energies, huh? The velocities seem fine. I was interested in the kinetic energies. And so that's going to come from Gm over R. So there's no square rooting here. We're just wondering what the potential energies will be for something sitting on the surface of the Earth, and then compare that to the potential energy of something sitting on the surface of the Moon. And so that's going to give us a factor of 80 times more. And then how do the R values compare? And this is going to be what, 3? So 80 divided maybe 30 times more, 25, 30 times. We're going to need 25, 30 times as much energy to launch something from Earth. Does that work out? 30, it does. 25 or, yeah, roughly. So yeah, the numbers actually look pretty good. So it does take, 25 times more energy, let's say, to launch something from the surface of the Earth compared with the Moon. That's a big savings in energy, right? Okay, this is kind of our last topic that we're going to be looking at, and that is power. And again, power is such an important concept, so really pay attention to the power discussion and take a look at those homework problems. Make sure that you're looking at these. The gravitational potential energy problems too, those are important too. So take a look at these last couple topics that we've looked at today. Anyway, I'm going to move on and start talking, I guess, a little bit about power. If there's any questions on this stuff can be tricky, so definitely stop by with what questions, whatever questions you've got. Power is an energy rate. So there's a couple questions we could ask. We could say whether, how much energy is something going to require? How much energy is it going to take to drive my car to the top of some mountain? How much energy is required to do that? That's a number that we could calculate based on potential energies and whatever. But then there's a second question, and that is, how much time is it going to take to drive there? So it's one thing to say, my car can come up with this much energy. It's another thing to say, it can come up with this much energy in this much time. So power involves the amount of energy. Now here it's listed as work, and work is one sort of energy quantity that we think in terms of. Work is transferring energy. So if I have a motor generating energy, that might be expressed in terms of how much work is it providing. And then I divide through by how much time it takes to find out what the power is. Now what they've done is they put a bar over the top, a big P is power, and the power, they're saying this is an average formula. So if this work is being done at a very steady rate over a time period, then the power is just uniform. But it's also possible that work was being done at a faster rate, and then the work rate slowed down, and then it picked up again. And so they're saying that if I just take total work done divided by the total time interval, that will give me an average value of power. Now, instantaneous power, instant by instant, what's the power of something? And it's the rate at which it is producing energy or transferring energy. So again, this is listed as dW dt. That's the rate at which work is being provided to the object. Now, in the standard system of units, power is watts, where 1 watt is equal to, 1 watt is equal to 1 joule per 1 second. Yeah, that works. Energy per time equals power. Now, you may have thought, well, watts, isn't watt an electrical unit? Watt is just a general unit in terms of power, in terms of the rate at which energy is being produced. So a watt shows up with all kinds of mechanical systems. That is the standard unit that we're supposed to be working in terms of. So power, it's saying here, can also be described at the rate at which energy is transformed. So dE dt, that's kind of the same formula. It's still an energy per time that we're thinking about. Now, just for a units check here, the British system of units, the basic unit for power is the foot-pound. So power is in terms of foot-pounds per second. In the British system, the official energy unit is the foot-pound. It's pushing with a pound over a foot. Now, in the system international units, a joule is a newton times a meter. It's 1 newton of force exerted over a meter of distance. So foot-pound lines right up with newton meters, and then dividing through by the time makes it a power. Now it says here, and this is kind of embarrassing, but it says that more often than not, we use horsepower. Really? Horsepower? Isn't that a little archaic? Haven't we maybe moved beyond using units of horsepower? So, yeah, that's funny that horsepower has stayed around so long. Now, 1 horsepower is defined as 550 foot-pounds per second within the British system. And if we convert into standard units, 1 horsepower is 746 watts. So I think we're just going to use watts. Okay, so again, the horsepower, that's kind of embarrassing that we still use that. I can't believe people still talk about how many horsepower this, how many horsepower that. We should just be everything in watts, right? Everything should be in watts. We don't need the BTU right? For heaters and range tops and stuff, British thermal units per hour. Let's just put everything in watts, and then we can compare everything ever so much easier. So again, generally power is some kind of energy divided by time. We can write that in this form, or we can write it as an instantaneous formula, dE dt. So that's instantaneous. Now, the power then, if we're relating it to a force that's doing work, then the power gets associated with that force also. So let's say we have some force F, and force F is providing work, and if we take that work and divide through by dt, that gives us the power, the rate at which that force is providing energy to the object that the force is acting on. So that becomes F dx, that's the work, divided by dt, and when you look at this, you realize, oh, dx dt, that's velocity. So the power associated with a particular force can be determined by taking that force value and multiplying by the velocity. Now that's kind of interesting. It means that if the same force is being applied, but the object's moving faster, that requires more power. So power power requirements are going to be based on how much force we need and how fast the object needs to be pushed. Now, moving back to an electrical example, a light bulb. Now, I listed this as 100 watts, but you know, the 100 watts are the old incandescent bulbs, and those have all been replaced. You know, I always had hesitancy about the fluorescent bulbs because the fluorescent bulbs had a little bit of mercury in them. But now we've got the bulbs based on diodes. What are those called? So we've got the new bulbs that use even less energy than the fluorescent bulbs did, and so all my lights are switched over from the old incandescents, and the current generation of bulbs, of light bulbs here are they often will be 1/10 or less, 1/10 or 1/20th of the power requirements for the lighting. So anyway, if we have a light bulb and it's listed at 100 watts, the 100 watts is 100 joules per second. So if we operate that light bulb for 20 seconds, the amount of energy being used is going to be power times time. It's been used at a rate of 100 joules per second, and if that's being used for 20 seconds, that's 2,000 joules. So when my kids were growing up, and they would leave lights turned on in the house, then I could stand there and go 100 joules, 200 joules, 300 joules, and kids say, "What are you counting, Dad?" And it's the energy that is going into that light bulb that nobody's using, because it's a 100-watt bulb, and for a 100-watt bulb, it's 100 joules every second. That's the requirement. All right, let's take a look at stair climbing power. We got a 60 kilogram person, and that 60 kilogram person is running up a flight of stairs, and they're going to run up that flight of stairs in 4 seconds. Good luck. That's a lot of stairs for 4 seconds. So they're running up the stairs in 4 seconds. The vertical height is 4.5 meters. They are really zipping up those stairs. Estimate the jogger's power output in watts, and I crossed out the horsepower. That's kind of embarrassing. How much energy does this require? So let's calculate the power and let's calculate the energy. All right, here's my diagram. So here is the ramp headed there. Now remember, it's back to this idea of it just really depends on elevation changes, right? It depends on age. So it's not so important how steep these stairs are. What's really important is how much potential energy the person has built up. So if we set h to be 4.5 meters, that's what they told us, and the person is propelling themselves. So the 60 kilogram person is lifting a 60 kilogram object themselves. up the stairs. That's 60 kilograms, and Earth's gravitational field. So if we say we need a potential energy increase of mgh, that works out to be 2646 joules. So that's how much energy we need. So that's energy requirements. And then what's the power if the person comes up with that much energy in just 4 seconds, and it worked out to be 661 watts. So that person is able to come up with 661 joules every second and put that energy towards propelling themselves up those stairs. All right, power is also required if we're going to have an acceleration. So let's think about this. If I have something moving at a constant speed, and there's no opposing force, you know, let's say there's a car, it's perfectly lubricated, all the bearings, and it's on a level surface. How much energy, and there's no air resistance, somehow it's aerodynamically built. It wouldn't require any energy to keep it moving. Now, we would need some energy to accelerate the car, but we wouldn't need any energy to keep it moving. Now, in reality, there is friction. And so a car needs to come up with enough energy to offset the force of friction. Now what we're going to do here is, instead of thinking in terms of energy, we're going to think in terms of power. What's the power requirement of a car? At what rate does it need to come up with energy, dW dt, if it's going to provide a driving force, pushing the car forward, of F multiplied by the car's velocity. Now again, they've drawn this as a dot product, and that's fine. It turns out that V and F are in the same direction, so we can just drop the dot product signs for this. Okay, so power needs of a car. Here we go with this example. We are going to be sending this car up this hill, and it says that the car's mass is 1,400 kilograms. The car climbs a 10-degree hill. That's a fairly steep, yeah, they say that. It's a fairly steep hill. 10 degrees is pretty steep, at a steady 80 kilometers per hour. So first of all, we want to drive up the hillside at a constant speed. What's it going to take? And then on the second one, what we want to do is we want to actually be accelerating up the hill. So that's going to require even more power we're going to have to come up with. Now, it says that there are resistive forces if we include, I guess this is like air resistance. They call it a retarding force. It's a resistive force on the car, and that's at 700 newtons throughout. So let's see what we've got. Here is my diagram. I'm doing all the forces in this. So here is the force, static friction, that's enabling the pavement to push forward on the tires of the car, and the car gets pulled along by that. So, you know, that all of that mechanism needs to be sturdy enough, because it's the tires attached to the axles that are going to pull the car along with it. So these static friction forces are going to pull the car up the hill. I've got this resistive force, I'm going to call it R. I've got components of gravity, mg cosine, mg sine, and I got a normal force. Now at constant speed, it's going to be mg sine. Well, I calculated all the forces. Yeah, these are the numbers given. I'll start here. 1,400 kilograms, 10 degrees, same stuff we said before. The 80 kilometers per hour works out to be 22.2 meters per second, and that retarding force, the resistive force, is 700 newtons. And so mg sine theta is 2382 newtons. I guess that one's important. Mg cosine is 13,500 newtons. I'm not sure if that's important. Now the force that the engine has got to provide at this contact point with the pavement, the force that we can trace back to the presence of the engine, it's actually a static friction force here, that force is going to have to offset the gravitational component and the resistive forces. Combining those together, I ended up with 3,082 newtons. Now we want to be able to go up the hill. Remember what we said in terms of power requirements. Not only do we have to be able to provide enough force, but we have to provide enough power so that we can apply this force and keep the car moving at some speed. So I need to know the force, which we've got, and I need to know the speed. Now in this example, the force is this value the whole way up, 3,082 newtons, and the speed is 22.2 meters per second. It's going to require 68,480 watts. Okay, so 68.5 kilowatts. So now I did do horsepower. I apologize for that. It turned out to be 92 horsepower that we need. So, you know, you can just take horsepower and since, what did we say a horsepower was? A horsepower was 746 watts. And so it's not so 746 watts. So a horsepower is about very, very roughly a kilowatt. So we're going to require 68,500 watts of power. All right, what happens now if we want the car to also accelerate? Okay, so the speed we're starting out at, 90 kilometers per hour, we're going faster, right? Okay, so we're going faster, we're going 25 meters per second, and we want to accelerate to 30.6, and we want to do that in 6 seconds, and we want to do it all while we're climbing the hill. That is asking a lot from our automobile. So that says the acceleration we need is 0.926 meters per second squared. Meters per second per second. Now, the additional force that we're going to need, MA is not a force. So let's be clear. MA is just information about how much mass and what the acceleration is. But remember, to accelerate at 0.926 meters per second, a mass of, where did it go? It was on the page before. 1,400? Was that it? 1,400 kilograms. So to accelerate 1,400 kilograms at that rate is going to require an additional MA. That is an additional 1,296 newtons. When we write down the laws of motion, that's what comes out. The force pushing the car up the hill needs to be as large as mg sine theta. We got to offset the gravitational component. We got to offset the air resistance, frictional effects, and we have to accelerate the car. That's a bigger force. Now, the force, it turns out, is still constant. So you go, well, fine. If the force is constant, can't my car just accelerate endlessly? And you go, well, it's one thing to ask what the force is and have the force be constant, but your car has to come up with enough power to allow for higher and higher speeds. There's going to be some speed at which the car engine can't provide the energy fast enough. So the engine maxes out. There's going to be an ultimate highest possible speed for a given amount of power in your engine. So just to kind of drive that home, the velocity is increasing, right? And the power is increasing. So as the speed goes up, we just have to come up with more and more power. Now did I plug numbers in? I don't think I did. I did! Yes! Okay, good. It's a sensible thing to do. I couldn't remember if I had. So the power that we need when we first start that acceleration is the force. Remember, the force is going to be 4,378 throughout at 25 meters per second. So that's 109 kilowatts I need initially, or 147 horsepower. What happens by the time I'm going 30.6 meters per second? So 30.6 meters per second. I mean, we're accelerating here from what, like 50 miles an hour, 55 to 65, something like that. So initially my 1,400 kilogram car is going to need the 147 horsepower. That's going to bump up to 180 by the time I'm going 65 or, between 65 and 70. So the power is going from 109 to 134 kilowatts. If my engine can only provide 134 kilowatts, that's it. It maxes out. It's not going to continue to accelerate anymore, not because of the force issue, but because of the velocity effect here. I can't come up with the energy fast enough to maintain, I don't have enough power to go any faster given the forces that are required. All right, there's a short section here. I'm going to say that we're through some of these really important parts. So the gravitational potential energy, definitely pay attention to that. All of the power examples too that we've looked at, especially that last one, that's a really good example to go through. Comparing a car going up a hill at constant velocity, how much power will that require, and then if you're going up at accelerated velocities, how is the power going to climb as you go faster and faster? And the power is going to be proportional to velocity. Okay, so as the velocity goes up, you're going to need a proportionally larger amount of power to provide for that. Okay. Here is just a diagram. You can think of this as a roller coaster diagram. It says that there's an object, they call objects particles, moving under the influence of a conservative force. So it's kind of like gravity. If the amount of energy that the object has is here, then the object would oscillate back and forth between these turning points. So with a given amount of energy and a given potential energy profile, can we go in and predict what the motion of the object might look like? So if we had this much energy, what would the options be? And with this much total energy, we could just sit at the bottom of that potential energy profile. With this much energy, we can oscillate back and forth here. What about this much energy? Well, with energy 2, we could oscillate back and forth here, or we could oscillate back and forth here. Those are possibilities with that much energy. If we have this much energy, energy 3, we could let go, and the object would be able to make it over that and make it over here. This is the assumption that all the forces are conservative. There's no air resistance, there's no friction. Now, if we get an energy profile gravitationally, then that's kind of the roller coaster example. But you remember, we have other conservative forces. So if these are electric or magnetic forces inside, say, a molecule, for example, then this might correspond to the kinetic and potential energy of the electrons. Now, in quantum mechanics, which we'll look at in Physics 4C, we find that the rules are a little different. It's possible for a particle with not enough energy, let's say we have an electron in a molecule held in place by the surrounding nuclei and the surrounding electrons, but there's a lower energy space for the electron, but it currently doesn't have enough energy to get past this peak in the energy profile. Quantum mechanically, the electron can still find its way there. There's still a finite probability, which we can calculate, that the electron will shift over to a different region of the energy profile. So that's kind of interesting, maybe something to look forward to as we get into Physics 4C. So yeah, there's just that one last diagram. Again, it's a nice example here. Make sure you're taking a good look at this. And then there's a summary of what we did in the chapter. Okay, so if you guys have questions, stop by and we can take a look at those.